Hi, folks. This is Heath. I hope y'all had a fantastic weekend. Um, we're covering the very last day of material for this course, so give yourselves a round of applause. We are making it to the end game in this course. So, what we're going to cover today, this section is called Motion in Space. We've already talked about the idea of launching a projectile where we give some object an initial velocity, but then once it's in the air, it's inert. There's no propulsion. There's no steering to it. It just follows a course of gravity from that point. And so the acceleration on the object is a constant. What we're going to look at here is a few examples of more complicated acceleration, where we have an object that has some kind of either propulsion or spin or charge or some kind of reason that would cause it to behave differently than a projectile. So let's look at some of these examples. Okay, we want to find the position vector for a particle that has this acceleration and this initial velocity in position. So the acceleration is, which is the second derivative of the position, is 14t, comma, sine t, comma, cosine of 2t. And so if we want to find the velocity, we'll have to integrate this. It'll be the integral of the acceleration. So when we integrate 14t, we get 7t squared. When we integrate sine of t, we get negative cosine of t. And when we integrate cosine of 2t, we get 1/2 sine of 2t. This is a u substitution problem where we have to set u equal to 2t, and then du becomes 2 dt, and then we have to take out a 1/2. So, but each of these involves a constant. This is 7t squared plus a constant. It's cosine of t plus a constant. 1/2 sine of 2t plus a constant. And we know that the initial condition at time 0, the velocity is equal to just the I vector. So velocity at time 0 will be 7 times 0 squared plus c1, negative cosine of 0 plus c2, and 1/2 sine of 0 plus c3, and that equals to 1, 0, 0. And so c1 has to equal 1, and be careful here, c2 has to equal to positive 1 also, because negative cosine of 0 is minus 1, and we need to change it back to a 0. C3 is equal to 0. So these are our constants. And so now we know that the velocity is 7t squared plus 1, negative cosine of t plus 1, 1/2 sine of 2t. The position then, which is the integral of the velocity, will be 7/3 t cubed plus t plus a constant again. The integral of negative cosine t is negative sine t plus t plus a constant. The integral of 1/2 sine of 2t is negative 1/4 cosine of 2t plus a constant. Another 2 comes out, so this becomes negative 1/4. And at time 0, the position is j. So r of 0 is 7/3 times 0 cubed plus 0 plus c1, negative sine of 0 plus 0 plus c2, negative 1/4 cosine of 0 plus c3, and that equals to 0, 1, 0. And so c1 is equal to 0, c2 is equal to 1, and c3 in this case has to cancel out a negative 1/4. c3 will be positive 1/4. And so our final answer to the question is to find the position vector. Is the vector r of t, which is 7/3 t cubed plus t plus 0, negative sine of t plus 1, plus t plus 1, and negative 1/4 cosine of 2t plus positive 1/4. Okay? All right, let's move on. Let's try another example. A force with a magnitude of 30 newtons acts directly upwards from the xy plane on an object with mass 6 kilometers. So here's our object, and we're going to apply a force of 30 newtons directly upward from the xy plane, so in the positive z direction. The object starts at the origin, so I drew this in the wrong place. Just move my axes. There we go. With an initial velocity of I minus j. Find its position function and its speed at time t. Okay. So the acceleration, we have to do a little bit of work here. The formula we're going to use to find the acceleration is, you've probably seen this formula before, F equals ma. This will give you the magnitude of the acceleration. This is a scalar formula because we only have magnitude for the force. So 30 is equal to 6a. And so the magnitude of the acceleration is equal to 5. But the direction of the acceleration is in the z direction. And so our acceleration vector is 0, 0, 5. So velocity is the integral of the acceleration vector, which will be c1, c2, 5t plus c3. And we're told at time 0, c1, c2, 5 times 0 plus c3 is equal to I minus j. And so c1 is equal to 1, c2 is equal to negative 1, and c3 is equal to 0. And so our velocity is 1, negative 1, 5t. So now we have to find the position function. So the position function is the integral of the velocity function, which is t plus a constant, negative t plus a constant, and 5 has t squared plus a constant. And we know that at time 0, 0 plus c1, 0 plus c2, 5 halves times 0 squared plus c3 is equal to the origin. Well, that makes it easy. c1, c2, and c3 are all equal to 0. And so our position vector is just t, negative t, and 5 halves t squared. Okay? So now we found the position function. The question is also asking for the speed. Speed is the magnitude of the velocity So that would be the square root of 1 squared plus negative 1 squared plus 5t quantity squared, which is the square root of 2 plus 25t squared. And that would be the speed at time t. So we have the position vector and we have the speed. Okay? So let's try one more, and then we'll move on to something else. A ball is thrown eastward into the air from the origin, east being in the direction of the positive x-axis. The initial velocity is 60I plus 48k, with the speed measured in feet per second. Okay, so let's see what's going on here. So here's our x, here's our y, here's our z direction. A ball starts at the origin. It's being thrown in the direction of the positive x-axis. But the initial velocity is 60I plus 48k. I is in the x direction, z is in the z direction. So the initial velocity is in the x-axis. But whoever threw it put a spin on the ball, which is causing the ball to accelerate southward in the negative j direction. And so as it's moving through the air, it's drifting towards the negative y-axis. There's a negative component for the acceleration. And so the ball is not going to land on the x-axis. The ball is spinning as it's floating through the air, and that spin is causing it to move in a diagonal direction. So where does the ball land, and with what speed does the ball hit the ground? Okay? So let's do some work here. We'll start with the acceleration vector. 0, negative 4, negative 32. The velocity vector is the integral of this, so it will be c1, negative 4t plus c2, and negative 32t plus c3. At time 0, we know what the initial velocity is. C1, 0 plus C2, 0 plus C3 is equal to 60, 0, 48. And so C1 is equal to 60, C2 is equal to 0, and C3 is equal to 48. And so that gives me a velocity vector of 60, negative 4t plus 0, and negative 32t plus 48. So now let's get the position vector. The position vector is the integral of the velocity vector. And so the integral of that will be 60t plus c1, negative 2t squared plus c2, negative 16t squared plus 48t plus c3. And because the ball started at the origin, R0 is equal to 0, 0, 0. And so all of my constant terms are going to be 0. Constant terms in this case match with the initial conditions, unless you have something tricky in your expression like an e to the t or a cosine of t that give you some value at t equals 0, and we don't have any of those things here. So the position is 60t plus 0, negative 2t squared plus 0, negative 16t squared plus 48t plus 0. All right. The ball lands when the z-coordinate is equal to 0 again. That's the z-coordinate. So we're going to say that negative 16t squared plus 48t is equal to 0. I'm going to factor out a 16t. And I'm left with t minus 4 is equal to 0. T minus 3, sorry. 16 times 3 is 48. And so we have two times. T equals 0 is the time that the ball left the ground. T equals 3 is the time that the ball landed. This is the time when the ball took off. So the question is, where does the ball land? The ball lands at R of 3, which is the point 60 times 3, which is 180. Negative 2 times 3 squared is negative 18. Negative 16 times 3 squared plus 48 times 3 is 0. 180 in the x direction, a little bit of drift in the negative y direction, and then landed back on the ground at 0. So that's the answer to this question. And the second question says, what is the speed when the ball hits the ground? Well, we have the velocity vector right here. Where am I going to squeeze this in? The velocity at time 3 is 60, negative 12. Negative 32 plus 48 is negative 48. Negative 32 times 3 plus 48 is negative 48. And so the speed is the magnitude of that velocity, which should be the square root of 60 squared plus 12 squared plus 48 squared. Whatever that calculates out to. All right. So we've done a few varieties of these moving object problems, and they're usually not too tricky. It's just a matter of integrating, remembering to solve for your constants at each step when you integrate, and working through the details of the problem. So they tend to involve a fair amount of writing, but usually the math isn't too bad. I want to get to one last topic, and let's finish this up. The tangential and normal components of acceleration. So we talked last time, this is just a little bit of review, that if we have an object that travels along some trajectory, and let's say the position of the object right now is this position, that there is a moving coordinate system containing the unit tangent vector, the unit normal vector, and then the unit binormal vector that moves along with the object. It's a first-person coordinate system that is geometrically isomorphic to I, J, and K, but instead of having a fixed location, the origin stays with a position, so that these three axes move along with the object is the idea. If we want to do the types of problems that we have been working on, these acceleration, velocity, position problems, in this alternate coordinate system, in this TNB coordinate system, we have to start by placing the acceleration vector into this coordinate system, which means we need to know, if we know what the acceleration vector is, how much of that acceleration vector is in the t direction, and how much of that acceleration vector is in the n direction. And we also need to know how much of the acceleration is in the b direction. And so if we have an acceleration vector in terms of I, J, and K, we want to know instead how much of that is in these directions instead. We want to make these conversions. We call this part the tangential component of acceleration. We call this part the normal component of acceleration. And it turns out this component is always, always, always 0. Because the coordinate system moves with the object, the acceleration is always in what's called the osculating plane. It's the plane that is made up of the t and the n vectors. It doesn't include b. We talked a little bit about the osculating plane in the last set of notes. So we don't have a symbol for the binormal component of acceleration. It just always turns out to be 0. But we have to be able to calculate these two formulas. This formula is pretty easy if you know how to calculate the t vector. It is the dot product of the acceleration with the t vector. And if you remember that the t vector itself is the derivative over the magnitude of the derivative, r prime, we could say this is r double prime dot product with r prime over r prime. The magnitude, we could write it that way. Okay? So we could use this formula here. It's just a dot product of the acceleration vector with the tangent vector, the unit tangent vector. The normal component of acceleration, we could also use the formula, same formula, a dot the normal vector, the unit normal vector, to calculate this component. But one of the things we mentioned last time is that sometimes it's difficult to calculate the normal vector. And so we're going to have this other trick, is that we're going to use the fact that t and n are perpendicular to each other, that this is a right angle, and therefore we can use the Pythagorean theorem. Once we have the Pythagorean theorem, the tangential component squared plus the normal component squared is equal to the acceleration squared. And so the normal component of acceleration is the square root of the magnitude of the acceleration minus the tangential component of the acceleration. We're just using the Pythagorean theorem to find an. Okay? I want to mention I'm presenting this a different way than the book is presenting this. There are formulas in the book. There are formulas 9 and 10 from this section, and you can look those up. And the formulas in the book are absolutely correct. There's nothing wrong with them. But they give you a formula for a sub n instead of using the Pythagorean theorem. And I just feel like the Pythagorean theorem is something that everybody understands. It's easy to remember. And so I'm trying to show you a formula that is simpler to memorize. I'm thinking ahead to, we are going to have to know this stuff for the final exam. And so I'm showing a different presentation than the presentation that's in the book. But the presentation that's in the book is absolutely correct. And if you want to use that, I have no problems with that. So you have an alternate way of doing these problems. You can use the formulas on page 9, not page 9 and 10, but formulas 9 and 10 from this section. And that works also. Okay? But the idea is a t vector is just a dot product of acceleration with a tangent vector. And then we're just going to use the fact that at and an are perpendicular, and the acceleration is the hypotenuse of the triangle. And we can use that trick to get the same answer. Okay? All right. So what I want to do, because I'm deviating from the book, this example, in my notes, I've numbered example 4 just because that's where it is consecutively, but it's identical to example 7 from the book. And in the book, they do it using the formulas they've introduced. And I want to just do the same example using this different set of formulas, just so that you can see that you get the same answers. So this is absolutely identical to an example that's in the book, but we're going to work it out in a different way. We have a particle that moves with this position vector, and we want to calculate the tangential and the normal components of the acceleration. Okay? So we first need to calculate the t vector, which is r prime over the magnitude of r prime. Okay? So r prime is 2t, 2t, 3t squared. The magnitude of that vector is the square root of 4t squared plus 4t squared plus 9t to the fourth, which is the square root of 8t squared plus 9t to the fourth. All right? And so the tangential component is 2t over 8t squared plus 9t to the fourth square root, comma 2t over square root of 8t squared plus 9t to the fourth. And now I'm writing kind of small. 9t to the fourth over, 3t squared over the square root of 8t squared plus 9t to the fourth. All right. So now we're going to calculate AT. The tangential component of acceleration. So that formula is equal to the acceleration vector dot with the unit tangent vector. The acceleration vector is the second derivative. We already have the first derivative here. The second derivative is 2, 2, 6t. And so when we dot these together, we're going to get 2 times this, so it will be 4t over the square root of 8t squared plus 9t to the fourth, plus 4t over the square root of 8t squared plus 9t to the fourth, plus 6t times 3t squared will be 18t to the third over the square root of 8t squared plus 9t to the fourth, which will equal to 8t plus 18t cubed over the square root of 8t squared plus 9t to the fourth. Okay? So that's the tangential component of acceleration. That's this one here. AT is 8t plus 18t cubed divided by the square root of 8t squared plus 9t to the fourth. So now we have to calculate the normal component of acceleration. And the trick is that we're going to use the Pythagorean theorem. We know that the AT, we already know that side. And we can figure out what this side is. The magnitude of the acceleration will be the square root of 2 squared plus 2 squared plus 6t squared. That's the square root of 4 plus 4 is 8. Plus 36t to the fourth. And that goes here. So this is square root of 8 plus 36t to the fourth. And this is this complicated formula here. 8t plus 18t cubed over the square root of 8t squared plus 9t to the fourth. So now we're going to square these and subtract them. So the hypotenuse squared is, just get rid of the square root, 8 plus 36t to the fourth. This term squared is going to be 8t plus 18t cubed divided by, squared, divided by 8t squared plus 9t to the fourth. When we square these, the square roots go away, but I do have to FOIL this out. Okay? So this is going to give me a little bit of a mess. And I'm not adding here, I'm subtracting here. And the reason why I'm subtracting is because we have the hypotenuse here. If a squared plus b squared equals c squared, then b squared equals to c squared minus a squared. And that's what we've got. We've got the hypotenuse. Oh, shoot. Didn't mean to do that. Hypotenuse squared minus one of the legs squared. We'll get the other leg. All right. So here I need a common denominator. So I'm going to have to multiply 8 plus 36t to the fourth times 8t squared plus 9t to the fourth over 8t squared plus 9t to the fourth. And this I'm just going to have to FOIL out. Minus, I'm going to be writing all over the logo. That's going to be hard to read, but it's the same thing. I'm just copying down this term. Is there a way I can... blank out that logo? Yeah, I can do that. Make it a little bit easier to read. Well, it doesn't. Yeah, it's better. All right. Minus 8t plus 18t cubed squared over 8t squared plus 9t to the fourth. Oh, all right. So I need some space to work this out. So I'm going to go back up here and do some work here. When I FOIL this out, first times first is 64t squared. Outer is 8 times 9t to the fourth is 72t to the fourth. Inner is 36t to the fourth times 8t squared. 36 times 8 is 288. And t to the fourth times t squared is t to the sixth. All right. And it just occurred to me that I've made an error here. That shouldn't have been t to the fourth. This should have just been t squared. I'm so sorry. Let me correct this. I bet you've been sitting in your chair screaming at me to fix this. This should be a square, and this should be a square. Come on, fix that. Oh, I apologize for that. So this will be t squared times t squared. That will be 288t to the fourth. And then last times last, this is 36t squared times 9t to the fourth is 324t to the sixth over 8t squared plus 9t to the fourth. Minus. Now we have to FOIL this out. First times first is 64t squared. Outer is 8 times 18 is 144 t to the fourth. Inner is also 144 t to the fourth. And last is 324, 18 times 18 is 324 t to the 6th over 8t squared plus 9t to the 4th. Okay? Well, the 64t squareds cancel. The 324t to the 6th is cancel. And the 288t to the 4th cancels with both of the 144t to the 4th. This is the only term that doesn't cancel. And so this is all that's left, is this part right here. And this is equal to the normal component squared. Remember, we're working through the Pythagorean theorem. We've squared the hypotenuse minus we've squared a leg. We have the other leg squared. And so we're going to finish up. AN is the square root of all of this, 72t to the 4th over 8t squared plus 9t to the 4th. Square root of 72 is 6 root 2. The square root of t to the 4th is t squared over the square root of 8t squared plus 9t to the 4th. All right. And this is exactly the correct answer that's in the book, but we've obtained it using a different set of formulas than the formulas in the book. And again, I apologize for screwing up the exponent over here. Let's try another example and hope I don't screw this next one up. Okay? This example is not in the book. Just working through the same kind of problem with just a different trajectory. Find the tangential and normal components of acceleration at time equals t equals 2 for this trajectory. R of t is equal to this trajectory here. So the first thing we need to do is we need to find the t vector. That's equal to r prime over the magnitude of r prime. Okay, so we can handle this. R prime is e to the negative t, square root of 2, e to the t. And the magnitude of that will be the square root of this term squared, so that's e to the negative 2t, plus this term squared, which is 2, plus this term squared, which is e to the 2t. Okay? And so the t vector at time 2 will be e to the negative 2 over the square root of e to the negative 4 plus 2 plus e to the 4th, comma, square root of 2 over all of this, square root of e to the negative 4 plus 2 plus e to the 4th, comma, e to the 2 over the square root of e to the negative 4th plus 2 plus e to the 4th. And so that's the first step. We have our tangential, our unit tangent vector. So the next step we need to do is find a t. That's the a vector dot with a t vector. So a is the second derivative here. So r double prime, which is the acceleration. The second derivative of e to the negative t is negative e to the negative t. Oh, shoot. This should be negative. This should be negative. This will be positive again. The derivative of negative 2 is 0. The derivative of e to the t is e to the t. There we go. All right. So we're going to dot product this vector with this vector at time 2. So at e to the negative 2 times e to the negative 2. When we multiply things with the same base, we add their exponents together. So we're going to get negative e to the negative 4. Square root of 2 times 0 is 0. E to the 2 times e to the 2 is e to the positive 4. All over this square root. Square root of e to the negative 4 plus 2 plus e to the 4th. Okay? All right. For the third step, we're going to use the Pythagorean theorem to find an. So an squared is equal to the magnitude of the acceleration squared minus at squared. The magnitude of the acceleration squared, when we take the magnitude, we would take square this and then take the square root. But we're squaring it, so the square root goes away. This is going to be e to the negative 2t, which is, again, where t equals 2. So e to the negative 4 plus e to the positive 4. Minus at squared, that's going to be negative e to the negative 4 plus e to the 4 divided by squared divided by this thing squared, which will be e to the negative 4 plus 2 plus e to the 4. All right. I need to get a common denominator here. So this will be e to the negative 4 plus e to the 4 times e to the negative 4 plus 2 plus e to the 4 over e to the negative 4 plus 2 plus e to the 4 minus negative e to the negative 4 plus e to the 4 squared over e to the negative 4 plus 2 plus e to the 4. All right, start multiplying out. Square foiling this here. E to the negative 4 times e to the negative 4 is e to the negative 8 plus 2e to the negative 4. E to the negative 4 times e to the positive 4 is 1. It's e to the 0. We add the exponents, and e to the 0 is 1. E to the 4 times e to the negative 4 is 1 again, plus 2e to the 4 plus e to the 8. Okay? Blank this out. So we've got some room. I hate doing this to the tech logo. Go Hokies, but we need the space. There we go. All right, minus, foil this out. Negative e to the 4th times negative e to the 4th is e to the 8, negative 8. Outer is going to be negative 1. Inner is going to be negative 1. And then last is going to be e to the 4th times e to the 4th is e to the 8th. All divided by e to the negative 4 plus 2 plus e to the 4. The e to the 8's cancel. The a to the 8's cancel. E to the negative 8's cancel. These don't cancel. This is minus a negative. So this is going to be plus 1 plus 1 plus 1 plus 1. It's actually going to be plus 4. All of this, I'm going to go back up here, is equal to 2e to the negative 4 plus 4 plus 2e to the positive 4 over e to the negative 4 plus 2 plus e to the positive 4. That's what we have here. 2e to the negative 4, 2e to the positive 4, plus 1 plus 1, plus 1 plus 1 is plus 4. But what happens here? If I factor out a 2 from the top, I've got e to the negative 4 plus 2 plus e to the positive 4 over e to the negative 4 plus 2 plus e to the 4. And all of this cancels. And so it turns out for this problem that we're still calculating an squared is equal to 2. And so an is just the square root of 2. Very simple answer to a complicated looking problem. Okay? So AT was complicated here, but an works out very simply. All right. All right. I made a couple of computational errors along the way, and I think I caught them all. But if you have any questions, let me know. I'm here for office hours today at 10:30, and then tonight I'm holding a Zoom class at 7 o'clock if you want to come by for that. And Wednesday we're going to be reviewing for the test. I will have an answer key for the practice test that I posted. I'll have an answer key up by then. All right. Y'all take care. Have a great day.